Hey guys, um, this is I'm gonna be covering the effective. Okay, so this is from chapter 24 of physics, capacitance. Basically, it says a fuel gauge uses capacitor to determine the height of the fuel in a tank, and the effective dielectric constants, the KF. So this is what we're doing. Changes from a value of 1. So it changes from when the tank is empty to a value of K when the tank is full. Each of the two rectangular plates has a width. So these two are the capacitor plates. So we have two capacitor plates in a parallel and the length of L. The height of the fuel between the plate is H. You can see there. So first, we are to derive an expression for K effective as a function of H. Cool. So first, first we can say that I'm doing a different color. We can say that C, the capacitance, is equal to the K epsilon naught multiplied by A over, where A is the area and then D is the distance. Okay, cool. So here, this is what we're looking for. Epsilon naught is just the permittivity of free space. So that's just a constant. So since we are looking at two capacitor plates in the parallel, we can then find CEQ or the CEQ or the capacitance equivalence. So we need from the capacitor from the capacitor equivalence we can find the effective K. Cool. So we can say that CEQ, or we'll just call it CEF, C effective, is equals to C. So there is from our from the directions says it changes from a value of 1 to when the tank is empty to a value of K when the tank is full. But this one, it's neither empty nor full. So there is a part where it has air in it, and there's also a part where it has fuel. So we can say that the capacitance is equal to the capacitance effective is equal to the capacitance between the air plus the capacitance where there's fuel. So we're gonna say C. We can just end up writing this as K effective. This is what we're searching for. And then we have our epsilon naught. And then we're gonna have our area times the distance. So area times sorry, our area over D. Okay, so the area for the whole thing is just gonna be length times width divided by is gonna be length times width divided by the D. The D is just the distance, so this would be our D right here. So it's going to be just length times width over D. So the length times the width divided by D. We're just going to say that LU is equal to A. So then we can go ahead and just write for the air. So we're going to say K air. And then we have our epsilon naught multiplied by the length. The length for the air is actually not just L, because we also have the height of the fuel. So we have to do for the length of the length. So for the length of the A, we're gonna have to do L minus H multiplied by the width all over the distance. And then we're gonna do the same for the fuel. So it's gonna be plus K fuel. And the reason why I'm doing plus is because the capacitance equivalence in parallel is going to be the capacitance 1 plus the second capacitance is equal to the capacitance equivalence. That's why I'm using C. So it's going to be K, and then it's going to be fuel Then I have epsilon naughts, but I did that poorly. Epsilon naughts multiplied by the length is just h. There, you can see it's just h. H times the width all over d. Cool. So now we have all of this. We're going to try and go ahead and solve for the k effect. So we actually know. So we know the k of air. It's set in our equation that it changes from a value of 1. So k air is actually just 1 here. So if k air is equal to 1, we can just go ahead and just rewrite this, right? This goes to 1, and then we can just cancel our our constants from both sides. So we can go ahead and just cancel epsilon naughts. We can cancel d. And we can go ahead and just cancel all the width. They're all the same width. And then this also cancels. So then we're going to be left with K effective is equal to, I'll just write it down. We're going to be left with K effective. We actually have L here. K effective times L is equal to, we have an L minus H. We have plus K fuel. Cool. So then we could actually just substitute, we could just redistribute this L right here, the left side. Distribute this L to both sides. So then this would give us 1 L over L is 1 minus H over L plus K fuel H over L. So now we've successfully, So now we have successfully put the K effective in terms of H. So this would actually. So for the second part, we're actually given a value here. So it says, what is the effective of dielectric constants if the tank is 3/4 full? So we are just going to go ahead and erase this part. So let's think about this. If the tank's 3/4 full, where does that show in our equation? It's going to be these. So when these are 3/4, what is the value of the K effective? And we're actually given a dielectric constant for the fuel. So K fuel is equal to 33. Cool. So let's go ahead and just do this real quick. So we have K effective is equal to 1 minus. You can do 3/4, or you can also do just 0.75. I like doing the 3/4. Plus K. The K fuel is actually 33. And then it's going to be 3/4 as well. So if we do the math here, grab my calculator. It's 1 minus 3/4 plus 33 3/4. So that's going to give us the K effective is going to be equals 25. That's our final answer.